Our next talk's by Kevin on CNNs on liquid argon.
Yeah, in reality, I could have shortened this entire thing down to like 3 acronyms, but instead I decided to have an incredibly long title just to be that precise while we're talking. So what I'm looking at in terms of data is data coming from liquid argon TPCs. How these detectors work are you have particle tracks and showers as they are moving through liquid argon. These do 2 things. They free up ionization along the track of the shower, and they emit luminescence. And if the rendering of these wire planes were correct, you would see that this drift field that we apply between the cathode and the anode wire planes drift the ionization across 2 induction planes and then into a collection plane. And yeah, we can image that on this image here on the right. This is actually just one of the 3 planes. So you see tracks. In this case, we know for a fact this is a neutrino event coming from an interaction vertice. And almost immediately after looking at this, you see, oh, wow, image analysis, convolutional neural networks, almost right away, but not quite. This gets a little bit complicated because on these 3 planes, in this case, these are oriented 45 degree angles from each other. And so if you were to look at any of these 3 images, the projection of the tracks onto the 3 create these kind of skewed looking images relative to each other. If I use my arbitrary geometry called the maze, you can see what I've done here is I have taken all of the charge collection from each of the 3 planes and encoded it to R, G, and B, and then created an image out of this. And so you can see here we've got induction, and then collection. And these are all the 3 data sets for the same event, but unlike real images, they're not on top of each other. The information relative to a single piece of charge that has been freed up and then drifted through the detector ends up in 3 different regions in the image. So it gets a little bit more complicated than simple image analysis, and I'll get back to that when we first start talking about the convolutional neural networks. What I'd like to talk about first are the 2 detectors that I'm working with. The first one is the microboon detector. This is the current generation scale liquid argon TPC. And this is part of our short baseline program looking for neutrino oscillations, although once again, that's not what I'm looking for. And in this case, what the geometry of it looks like is we have the 3 planes we talked about earlier, 2 induction planes, 1 collection plane. And the one thing that I neglected to mention, because I was really bad about talking about it, is when we orient these images, the x-axis is the wire number coming from the plane, and the y-axis is the time of the readout. So if you were to take a vertical slice of one of these images, it's just the waveform as being read out from a single channel. What we've done is just stack all of these together in order to create these images. So if I was to take the raw readout time, which is 9,600 digitizations, and the 3,600 wires, that's a 3 by 9,600 by 3,600 image. They're huge. And this is to cover the total drift length of particles coming out of the detector. And so if you have a single trigger, you are guaranteed to get the full track, plus or minus 1 more on either side. Whenever we talk about liquid argon TPCs, we would like to develop workflows and analyses that not only work for what we are currently using, but the future next generation. And in this case, the next generation liquid argon TPC project is called DUNE, the Deep Underground Neutrino Experiment. And this will consist of a much larger set of these detectors. We typically arrange these in terms of APAs or anode plane assemblies. And so this is going to end up being a full order of magnitude more data coming out. So what I would like to look for in these detectors and to create an analysis for is proton decay. It's not the main physics goal of liquid argon TPC program, but it's something fun and interesting to look at, and we can do it. The candidate paper that we look at is we call the Bueno paper that outlines the channels that we should be sensitive to, and the 3 that I am currently looking at are P2, K plus nu bar, mu plus gamma, and E plus pi 0. And we expect to be sensitive to these to the extent that we can place upper limits on the lifetime for each of these particular branching ratios. What I want to fetch out from analysis and how this factors into the endpoint goal of getting a lifetime out are these variables in red, with the green being the objective variable that we use to constrain the full system. So I need to know not only the number of candidate events that I fetch out of a given data sample, but the expected background rate, luminosity on the detector, and the various efficiencies related to not only the detector itself, but my analysis. Not to mention, since this is a Bayesian analysis, what the Monte Carlo variables in terms of background rate go into it. For the two experiments, this is slightly different. For microboom, this is a detector sitting on the surface, and so we end up picking up a whole bunch of cosmics to the extent of about 11 per 1 data frame that we get. And this is an example image here. You can almost see it. These small tracks are the various backgrounds as they are interacting in the detector. Dune will be slightly different. It's going to be underground by about a mile. And so I'd expect much, much less background rate, and primarily from atmospheric neutrinos, but also something to be concerned about when you're looking for very, very rare decays. So my strategy is, and this is something that I like to put on slides because I never hear from people who are like, we're using convolutional neural networks to tackle a problem. This is the big picture where it factors in. So if you have input data, and in this case, I put down the microboom dimensions. In order to deal with these absolutely massive images, I'd like to downsize it. Currently, I'm using a fairly simple algorithm to just detect, pixel height, but it's not going to work once I put the cosmics back in. So I want to move towards using LSTM at some point in the future, although that's not today. Once that's been downsized, I'd like to look for multi-class particle IDs. So I'd like to be able to tag the various daughter particles coming from rare decay events. Once I have a candidate selection, I would like to use semantic segmentation to fetch out the relevant pixels, and then using that, apply my final cuts, and then get to the lifetime. So yeah, to get the final, not only the background number of events, but the total number of candidate events. This sits on top of a large body of work. I'm hardly the first person to deploy convolutional neural networks in microboom, and in particular, the previous analysis comes from the neutrino oscillations low energy excess group. This was headed up by a group from Nevis and MIT, and they recently published a paper, and I've linked the archive version of it there. And what that provides for us is a whole bunch of framework going in, mostly CAFE and OpenCV-based image preprocessing. They also have a 3-plane treatment that I looked at when I first started my analysis, and then I decided to go a different direction. Not to mention some baselines in terms of what we can expect from single particle identification and the semantic segmentation that we'll do later. When I talk about the 3 planes, so since I can't do a convolution over each pixel and expect to fetch out similar information expect to have spatial relativity when I'm going between the 3 planes. What the Nevis MIT paper suggested was use something like Siamese towers. So the idea is you break a single image into its 3 constituent parts. A separate branch of your neural network analyzes each part of it. Everything gets concatenated back together again and then thrown into the trunk of your network for final analysis, and then you do your classification on the output. This was not only used in microboom, but when we looked over some of the previous work from NOVA, another neutrino experiment, they also have this in their analyses. In fact, I linked the archive to the relevant paper there at the bottom. What I did, instead of doing that as an attempt to improve on this model, is I moved, instead of doing 3 separate networks, I wanted to do 3D convolution, so convolving over each of the planes. And I wanted to fetch out individual features from each plane and then do an analysis that uses the combined features from all 3 of them to do refinement, and then finally do your classification. So what we came up with for this is a model where you have your input. This goes to what I call the single plane stages. So I do 3D convolutions that are constrained to 1 plane at a time. Each of these consists of modules that is your 3D convolution, your 2D max pooling, kernel size and the stride size of those are designed to spatially contract the images down until I get to my fourth layer where I do 3D convolutions and then start fetching out features from all three planes. And I basically repeat that a couple more times until I get to my final classification. And the benefit of that is the weights that I use for analyzing any one of the planes can be applied to either of the two other planes. So I'm saving on a little bit of computational efficiency. The software stack, and I absolutely love putting up this slide because this kind of provides for me full transparency because everything that is involved in this analysis should be somewhere in here. Involves data is produced in Larsoft, which is this framework that is designed for all the liquid argon TPC experiments. This then goes to a HDF5 conversion utility that we created called Kevlar because it's slightly narcissistic. This creates HDF5 data that is then passed to another library called DL Data Validation Toolkit that does our pre-processing. This is then passed to the final library, which I just surreptitiously call the Proton Decay study. And this depends on Keras and TensorFlow. Links to each of these packages are here at the bottom in case you want to check them out. We can't, because we haven't had permission yet to show final results, show the actual numbers on these plots, and I apologize, but we can show what we've gotten out of this. So what I've done here is I've taken the network and broken it up into stages and then pre-trained each stage one at a time. So if I was to look at stage 0, this is just the first module, the fully connected layer in the input. Stage 1 has the first 2 modules, the fully connected layer in the input, etc. So when I hit stage 3, which is where the 3D convolutions start looking over all three planes, you can see in the accuracy we get this massive jump. And that shows that we actually do need all three layers and we do need some special treatment. So we're heading in the right direction. We know that. We just haven't gotten to a result yet. The next thing that we're working on is we would like to deploy this in a way that makes it sensitive to inline analyses in the future. So we developed a partnership with Micron, who are based here in Seattle. They've given us a few cards that we are working on moving our neural networks to. And we're hoping what we can do here is create either a trigger or an inline system for detecting proton decay or other rare decay processes before they hit other triggers coming from, say, inline events. And currently that is a work in progress. So, in conclusion, we're working on doing proton decay in liquid argon TPCs. We've got 2 experiments in mind. And whatever we're doing so far has to work with both of them, so we have to work with very large data sets and look at the backgrounds in particular. One of the things that we are looking at improving most of all is this multiplanar data and using the network architecture to tackle that particular problem. And we know that we're going in the right direction because we saw that accuracy jump. And then moving this to FPGAs at some point in the future for in-time or near-line analysis with more results to come in the future. Thank you very much.
I have a question about detector, about timing resolution of detector. I mean, you see at the end, you see static anything, or it's like moving.
So the full drift time that it takes, so the full drift time it takes for the charges to reach the planes is on the order of milliseconds. Interaction time is much shorter than that. So really what you're getting is a snapshot of a very static point of time as the drift to the detector.
So basically you have one snapshot for one loop.
Yeah. One snapshot, 3 projections. Yeah.
For this analysis, I'm not familiar with the analysis. So this is an event level ID from Argon, right? So you identify the whole event, right? Do you need? Do you need to get kinematics for each invisible particle for this analysis? And if yes, how are you planning? Do you plan to do one architecture, or are you planning to automate it?
Okay. So back to workflow really quickly. Yes, we need kinematics because at some point I need to make sure that the total energy is below the proton energy plus or minus the burning. I mean, that's basically just your one cut thing, right? So what I want to do, and we know from the neutrino analysis that you do have a successful kinetic segmentation network in place, is to go back and redo that, tag the individual pixels, and then do an energy summation over pixel and use that to determine our kinetics.
To identify the two different objects.
Yeah,
Right.
yeah. So step 1, classification, step 2, tagging.
How long do you have with the PGA step?
That's a really good question. I don't know the answer for you, so I don't know.
What?
We should have, well, that is a good question. Sorry, I'm staring at my boss right now. He's smiling at me.
That's what I'm planning to have available.
Yeah. It depends on a lot of things. All right, let's thank the speaker again.